Arrhenius equation. This is the Arrhenius equation. It relates the rate constant with the activation energy. K, rate constant, equal to AE to the power of negative activation energy over RT. K is the rate constant, A, the frequency factor, E is the base of natural log, EA activation energy, R is the gas constant, use the value 8.314 joule per mole per Kelvin, and T is the temperature. This temperature must be in Kelvin as the unit for gas constant is per Kelvin. And then put ln into this Arrhenius equation, you'll get ln K equal to ln A minus activation energy over R times 1 over T. The temperature, the larger the value of K, thus the rate of reaction increase. It shows that the temperature affects the rate by affecting the rate constant. This is the Arrhenius equation. K equal AE to the power of negative activation energy over RT, and F equal to E to the power of negative activation energy over RT. The F is the fraction of molecular collisions with energy greater or equal to activation energy. When the temperature increases, the average speed of particles increases because it gets enough kinetic energy from the high temperature. Thus, the collision frequency also increases. But only those collisions with enough energy, more than activation energy, can lead to reaction. The temperature rise enlarge the fraction. Temperature rise enlarge this value of F, fraction of collision, with enough energy to exceed the activation energy. The magnitude of both activation energy and temperature affect the fraction of sufficiently energetic collision. So higher temperature, larger K value, larger rate constant, thus the rate of reaction increase. If we have larger activation energy, smaller rate constant, the rate of reaction decrease. From this Arrhenius equation, you can put ln. You put ln K minus ln A equal to negative EA over R, activation energy over R times 1 over T. And then if ln K minus A, you move the ln A to the right side, it will become ln K equals to negative activation energy over R times 1 over T plus ln A. And you can compare this equation with y equal to mx plus c. The y is ln K, m, the gradient, equals to negative activation energy over R. The x is 1 over T, 1 over temperature, and the c is ln A. So this is the graph for Arrhenius equation. Ln K on the y-axis, this is y ln K, and x-axis 1 over T. And the gradient here, if you calculate the gradient here, that gradient is equal to activation energy, negative activation energy over R. And the C here, ln A, here is the C, the intersection of this line with the y-axis. Example, the rate constant for decomposition of nitrous oxide into nitrogen molecule and oxygen atom has been measured at different temperatures. Determine graphically the activation energy for the reaction. Here we have the value of K, rate constant values, and the temperature. Now we need to plot a graph. The graph here, we need to find the activation energy. So we need to plot the graph of ln K on the y-axis and 1 over temperature on the x-axis. So you have to construct new table for ln K and then construct new table for 1 over T. Make sure your temperature must be in Kelvin because the gas constant R use the unit Kelvin, so temperature must be in Kelvin. So this temperature, degrees Celsius, change to Kelvin first and then 1 over T values here. Now you have to plot the graph ln K versus 1 over T. How do you know whether you have to plot ln K versus 1 over T? Because we need to find the activation energy from the graph. Because we know that the gradient equal to negative activation energy over R. So that's how you know you have to plot ln K versus 1 over T. Now plot the graph and you get the slope. This here, this is the negative gradient. So slope equals negative activation energy over R. And then your value here, when you calculate the gradient, you get this value. And you know that the gradient is equal to negative activation energy over R. So we have the R constant, gas constant R, 8.314 joule per Kelvin mole. Substitute R here and we need to find the activation energy and you get the gradient. And then solve this equation and you will get 2.4 times 10 to the power of 5 joule per mole, and you can change it to kilojoule per mole. That is the activation energy. The question, does it ask for joule per mole or kilojoule per mole? So it's up to you to leave it in joule or kilojoule. If we know the rate constant at 2 different temperatures, so for this one, we only know for 1 temperature. But if we know rate constant at 2 different temperatures, you can use this equation. Because if you have 2 temperatures, ln K2 equal ln A minus activation energy over R times 1 over temperature 2. And then ln K1 equals ln A minus activation energy over R times 1 over temperature 1. If you have 2 temperatures, combine this, it will become ln K2 over K1 equals to negative EA over R times 1 over temperature 2 minus 1 over temperature 1. You can use this equation if you have 2 different temperatures. Example, the decomposition of HI has rate constant. So now you have 2 rate constant and you have 2 different temperatures. What is the activation energy of this reaction in kilojoule per mole? So your activation energy answer must be in kilojoule per mole. You have 2 different temperatures, you have 2 different rate constants, and you can use this equation because this equation you can substitute 2 different rate constants and 2 different temperatures. So when you use that, make sure change this temperature of degrees Celsius to Kelvin first, and you get this Kelvin, 781.15 Kelvin and 813.15 Kelvin. Temperature 1, temperature 2, substitute into that equation. Both rate constants given in the question, just substitute into that equation, and the gas constant substitute 8.314 joule per mole per Kelvin, and you will get the value of activation energy equals to 183311 joule per mole. And the question asks in kilojoule per mole, so you have to change in kilojoule per mole. It will be 183.3 kilojoule per mole. Thank you.